Alex here again, and welcome to part 2 of our RAMPS DUE conversion. This is a video where we're going to get into the actual hardware mods. Hang on, my stupid camera's going out of focus. See if that works. So here's the deal with this. Let me lay this all out front. The actual modifications are not that difficult, depending on how you want to do it. You just have to make sure that you do it right so that nothing dangerous happens, and so you don't ruin your gear, or your computer, or your hub, or something like that. And even if you do it right, there's always danger with these types of modifications, so double check, triple check everything. I think I mentioned in the last video that I actually did this modification twice. The first board was just like a really cheap RAMPS clone that I grabbed for a couple bucks off of Banggood. And there was a flaw in that board that's fairly well known, and when I did all the modifications and then plugged it into my USB hub, the protection tripped on the hub and my computer shut down. Did a point-to-point test with a meter, and I found out that the board was no good. So I did it again on another board. But that was fine, because it gave me an opportunity to show you both methods of doing it. So that's just to say that there are dangers, and even if you do everything right, it might be screwed up anyway, so be very careful. Second part is, if you do the mods wrong, and you, for example, like jumper a 5-volt pin to where you're supposed to have 3 volts, or you forget to cut one of the pins, or you jumper something wrong, and you end up putting high voltage on a low voltage input, you're going to fry your DUE. And then the third problem, well, I guess there's 4 problems. The third problem is, like, all of the RAMPS issues still apply, like all the thermal issues, the polyfuse issues, some of the, you know, all the things that I covered in a RAMPS series where you might have improper etch patterns, then your jumpers don't work, like all that still applies. And then the final problem is we're not level shifting our 3.3 volt logic from our DUE to 5 volt logic that some of our components expect. So some of them might not work well, and some of them work fine, and I will cover some of that. But the parts that won't work well are the MOSFETs, because the MOSFETs that come with a lot of the RAMPS boards, clones or genuine, are really not good enough for what they were meant to be doing, either shut down, melt down, or catch fire. But the problem is even worse now because we're putting less voltage on the gate, which switches them on even less, which causes more thermal problems. So you definitely won't be able to use the MOSFETs that are on the board unless they have been upgraded from the factory. And even then, they're not going to be upgraded to 3.3 volt logic FETs. They're just going to be upgraded to FETs that might work at that logic voltage. And when we get to the section on MOSFETs, I'll explain further. Now, as always with these types of things, I'm going to go into excruciating detail. But as you know, when I do something technical like that, I try to do it in outline form, make it modular, and then put a time map underneath in the description of the video so that you can click on those links and skip back and forth to the sections that you might need to review, or the sections that you might not understand and have to watch a few times, or just to skip things that you already know after you've watched it. I will also have a TLDR summary section at the end that briefly mentions all of the issues and what you have to do, and then you can always go back and click on the time index and find the parts where I go into detail if that pertains to you. So with no further ado, let's look at modifying our DUE. Now, let me give a little credit up front here. The first person I saw that really kind of made these modifications gel in a way that people could understand was Andrew BCN, or Andre from Spain. He's a RepRap open source enthusiast, and it was really the first guy on the RepRap forums that I saw a few years back that made these, rolled into a form that was accessible and usable for people. So I just wanted to give him a little nod up front. I'm not going to be using his mods exactly, but if you wanted to look for an alternate method or an alternate explanation, you can go ahead and check his posts out on the reprap.org. But hopefully what I present here is a little bit more user-friendly. Also, I should note that reprap.org forum user CX Andy has a company that rolled a lot of these changes into a RAMPS variation that he designed. There are open source files for all of that, the bill of materials, the board files, the schematics, everything on reprap.org if you want to look for it. It's called Smart RAMPS. He also made a profile for Marlin, so it should work out of the box. But also be warned that that board does not solve a lot of the logic level problems that I'll get into at the end of this video, so bear that in mind. Consequently, he's also the fellow that sells the AZ SMZ 32-bit boards, And he does poke around on the forums every once in a while to support the smart ramps and some other things. So just look for CX Andy as the handle, and you should be able to dig up his posts pretty easily. So first I'm going to lay out all the steps, which are right here. Then I'm going to break them down and explain what goes on behind those steps. Then I'm going to show you how to do it. Step number one, basically we're converting our ramps to a 3.3 logic board instead of a 5-volt logic board. You can keep it 5-volt logic and instead change your peripherals, but that adds additional difficulties, and this is the easiest way to do it. So after we're done with that, we're going to jumper 3.3 volts to the ramp's 5-volt bus. Then we need to cut any of the ramp's unused pins that are different on the Duo than they are on Omega, so that we can reuse those pins for things that we need, which are specifically jumpers for our thermistors. And then we can also add additional jumpers off of our 5-volt rail from our DUE to 5-volt peripherals if that's something you require. And we definitely have to replace the MOSFETs if you want it to actually function as a printer. Some other variations on these modifications, you can, instead of converting the ramps to a 3.3 volt logic board, you can leave the 5-volt logic and instead level shift your externals. I won't be covering that because it's very specific to what you're going to be using and what's going out, what's going in. As I mentioned before, you can also 5-volt jumper for your servos and make sure that they work with your 3.3 volt PWM. Or you can leave 5 volts on some of the pins and cut the traces to isolate those particular parts of the PC board. But again, that's dependent on what peripherals you're doing that for and which pins they're taking 5 volts from, if it's the aux4 or the aux2 header or whatever. So that's not something I'm going to cover because that's a specific mod and not a general mod. And then a few other things you may want to consider. I'm just going to throw these out there so that you don't think about it later and say, duh, I should have done that while I had the board taken apart. While you have everything apart, you can do a higher voltage conversion, 24 volts or whatever. You can use a switch mode power supply, little sub board, and wire that with jumpers off of your board to get your 24 volts or whatever higher voltage down to a level that's not going to pop your Duo. Now, that's useful if you want to backfeed your Duo power from your ramps board. If you don't care about feeding that board power separately, then don't worry about it. You can also use this as an opportunity to bust out those other I2C pins, which is your 2-wire bus. It's very useful for various different things, including I2C bus EPROMs. Now, as I mentioned before, your Duo does not have an EPROM on it. I don't personally use the EPROM for very much, and I can live without it. But if that's something that you are interested in, you can get for a couple bucks a little EPROM adapter and then hook that up to your either I2C pins that are broken out on the ramps, or if you already have something in there, like a display or something like that, you can bust out those 2 unused I2C pins, assign them in your firmware, and run your EPROM off of that. Of course, as you may know, the I2C bus is meant to work with a bunch of daisy-chained peripherals, so you don't necessarily need to bust out your second header, but we only have the 2 connector pins off of the ramps, so you would have to make yourself some kind of hardware jumper header, etc. First order of business is to look at the pin designations. Now, this is the pinout for the Arduino DUE on the left and the Mega on the right. And these pin maps are actually incorrect, but they're good enough for what we're going to be using. Let me mark in red the pins that we're either going to be cutting or not using, and that's these right here. And I'll turn that sideways so you can see it a little bit clearer. So these 4 pins on the upper left right here, those are analog pins on the Mega, but not on the DUE. So we're not going to be using those. You might as well cut them so that we don't have any problems. This pin right here is our 5-volt pin, so we're going to be cutting that since it'll be bridged to 3. And then these pins up top, they're not used on either the DUE or the Mega, so we can just ignore them. Same for these pins down here. This is our I2C bus that's not used on the ramps. You can keep that in mind for the future for a couple mods. And then over on the aux4, well, what would be the aux4 header on the ramps, these are also our 5-volt pins. We're going to cut those so that they're not attached to the ramps, but then I'm going to run a jumper off of those 2 pins so that we can go around the board with a little DuPont header and then use that to kind of power whatever 5-volt peripherals we might choose, like the backlight for a display or something like that. Now let's look at the board traces. This is a very confusing spaghetti map that just shows the top and the bottom traces on the RAMPS board. And the reason I'm doing this is so that you understand what we're doing and then maybe can get a concept of what we want to change if you want to do a different type of modification. So if I lighten that up a little bit and add some transparency, it makes it a little bit more sense. And then let me just highlight the major 5-volt rails that we're talking about here. Now, mind you, this is not all the 5-volt rails, because you can see from each of these major rails, it branches off into, smaller little traces that we can follow up and trace this here, blah, but it's a huge mess, so we don't really have to worry about that. One that you might want to pay attention to is right down here. These are the traces for your servos, and those are on a completely separate bus. So you can run 5 volts to the center header on the left side there, and that'll supply completely isolated 5 volts to those 4 pins on the right that are supposed to go to your servos. You can either run those to your servos if you want, as long as they work with the 3.3 volt PWM signal, or you can just use that as a header to distribute 5 volts around to different peripherals, whatever. That's all optional, but I figured I would mention it because that is a nice, convenient little spot. Okay, let's move on from how the pin map for our Duo applies to the pin map for our RAMPS board. Now, here's what they look like side by side. It's a little confusing, but don't worry, it's not actually all that complicated. What we're going to do in our first step here is we need to take all of the pins that are feeding 5 volts from the Duo to the ramps, and we're going to remove those pins in some way. We can either desolder them or just cut them, or you can cut the traces, etc., etc. We are just going to be snipping them off because I think that's the simplest and the easiest to undo. If you want, you could just solder a new pin in there. Specifically, what we're talking about is right here. If you look on the diagram on the left, the upper left-hand X with the little orange arrow on it, that's our 5-volt pin that's going bye-bye, and then we are going to bridge our 3.3-volt pin from our Mega to that 5-volt pin, so then we have 3.3 volts on the 5-volt rail. And then those pins on the bottom right that are feeding 5 volts from the double rail header, we are going to clip those off so that they're not feeding into the RAMPS board, and we're going to put a little DuPont jumper so that we can send that to whatever peripherals we need to run at 5 volts. Next step is these 4 pins that were analog pins on our Mega. They are not. They are our digital audio converter, and they are a CAN bus on the Duo, so we're going to snip those off. And on the header next to that, we're going to run our little jumpers for our thermistors, because those are not in the same place since the pin designations are wrong. Then, where you see the big circle and X in purple, those are our MOSFETs, which are not going to work, so we will have to replace those. And finally, like I mentioned, our extra step, we can take that 5-volt rail that was originally running to the ramps and then just run it to the servo header so that our 4 little servo pins are going to be 5 volts for whatever it is we need them for. Again, that's optional. So now we have the eternal question of which RAMPS board to use. Now, at its heart, this video is for people who already have a RAMPS and already have a Duo and want to reuse their parts and just modify them so that they work together. Not meant to like go out and buy all of those parts because, there are probably better options out there. But in terms of which ramps will work and which ramps won't work, well, we're doing a bunch of modification anyway, so pretty much any old ramp that doesn't have technical errors will work fine. It's just a matter of how many things you want to have to solder or desolder. So you can go back to my RAMPS series, I think it's part 1, where I do the review of a bunch of different boards just to show you what some of the issues are that might come up. Make sure all of your connectors are good. Make sure you don't have polyfuse problems. And then preferably choose a board that has upgraded MOSFETs on it. Now, I haven't found any of the boards that have 3.3 volt MOSFETs on them, but even a lot of the cheap RAMPS boards these days have been upgraded to IRF 3205 MOSFETs. And while I'm not sure those will handle all the current you need for like a hotbed without overheating, I know they will at least turn on, so you could always use an external MOSFET to run your bed if you wanted to and you had those FETs on your board. And it goes without saying, if you're going to be doing like a 24 volt mod while you're doing this, you want to find one that already has 24 volt compatible components on it to save yourself a little bit of time and effort. Now here's a problem I ran into. With doing all these modifications and review videos, I'm running out of RAMPS boards. I have a bunch of blank RAMPS PCBs, which I don't have time to build up. And then I have this Ziltech one that I'm actually saving for another project. And then in addition to that, I have an entire bin of, quasi-working RAMPS boards that I pulled apart in the video, either yanked parts off of, or they were just crap. So what I had left was a couple of these Chinese boards that I warned people away from in my review videos because they were built really poorly, and it turns out that was a good warning because they ended up, well, at least the one that I used ended up not being any good. So I ended up doing it on this RAMPS 1.6 board that I had grabbed for that review, and that worked out okay. One of the benefits was that at least I knew that the bed MOSFET was going to be okay-ish for a hot-end MOSFET, and I could do that without replacing any of the FETs on the board and save myself a little time and get some of my other freaking projects edited, and that's this one right here. Now, the additional step that I had to take with that is that since this MOSFET is assigned to the bed header, I had to reassign the gate pin of the MOSFET in the software to the hot end pin and then run the hot end off of the bed connector. So if that's something you're interested in, that's what you're going to have to do in Marlin firmware. As a result, I won't be able to run a heat bed for the test without replacing some of the MOSFETs, but that is something, if I were going to be doing a permanent modification, you could easily do. But if you recall from my 1.6 RAMPS review, you know that some of these headers were so bent that I couldn't even get drivers in there, so I had to go ahead and loosen up the solder on those and straighten them out, which was a pain in the butt, but it ended up working fine. Looked up the datasheet for the MOSFET that's on the board, and the ratings were a little bit pie in the sky, and I was thinking they probably didn't design this FET from scratch. They probably cloned somebody else's. So I did a little poking around and find out it's probably a clone of this Ixies MOSFET. So if you're going to be looking for a reference, I would use that reference because the ratings seem to be a little bit more realistic than a WSK datasheet. And just a fair word of warning, sometimes people have problems with the 1.5 and the 1.6 boards in that they are not in complete GPL compliance, in that they didn't provide updated board etch pattern files. But technically, that's not a requirement as long as they annotate the changes and put the information up. So they are considered by the open source community to be a variation on the RAMPS 1.4 board that simply have surface mount MOSFETs and upgraded headers. As a result, just so you know, if you're going to be using one of these, the schematics are still identical, the pin maps are still identical, and the parts are still basically identical except for the surface mount MOSFETs and the connector on the 1.6, and the fact that they use surface mount fuses instead of polyfuses to save room on the board and to get rid of the polyfuse problems. The only thing different is the board layout slightly because of the MOSFETs and some things they had to move, but everything else about the RAMPS applies to those as well. Okay, on to modifying our board. Now, there are two different methods that I'm going to cover. One is heating up the pins and pushing them through to the other side of the board, and the other is just clipping them. So first, let's do the heat and push method. This method's a little bit cleaner, but a little bit more difficult. It's nice because you can push the pins through to the other side of the board and then use them as a jumper rather than having to solder your jumpers on. And all we're doing is taking these pins, like the 5-volt pin, and we're going to shove that through to the other side after we heat it up with the soldering iron, and then put a little bit of a blob of solder on there to make sure we have good connection. So I just kind of lightly clamp this in a vise, and as you can see right here, I'm using a screwdriver on the one side and then heating up the solder joint on the other, and just kind of like poking it through. And that's it. You could also shove it through with pliers or whatever. Then I just take a little bit of a dab of solder and put it on the other side just to make sure that we have a good connection with both planes on the board. And that lets us use these nice little F to F jumpers to make our connections. But the easier method right here is the snip method, which, just as it implies, means you're just going to be cutting the pins that you don't need off. And then if you want them back at some point in time, you can replace them with good pins. The third method would be selectively scratching out board traces, but that's much more permanent and you have much more of a chance of screwing something up, so that's why I didn't include that one. So after we've snipped our pins off, then we have to bridge the 5-volt and the 3.3-volt pins. I found the easiest way to do that is just to put a little bit of a blob of solder to connect those on the top side of the board. And then if we're using multiple thermistors, we only have a hard connection on a trace for the one thermistor. So if you want to use the other two, you're going to take those pins that we clipped from the ADC or the CAN bus, and we're going to jumper those over the board onto the aux pins that correspond to those, and I'll show you that in the summary section. And then if you're going to be hooking up a 5-volt display or a panel or something like that, you're going to have to get power to it somehow. So I just soldered one of these DuPont jumpers to the 5-volt header on aux 4 and run that around the board and to the connectors for that, which is a real simple way to do it. And just to show you what that looks like on the schematic, right there are the 5-volt pins that we're going to be using. Now, this is the only part that's I think is actually in any way difficult, and that's replacing the MOSFETs. Now, obviously, you don't have to replace them all if you're not using them all, but whichever ones you're using, you definitely need to upgrade those. Now, I know from testing that the IRL-S and IRL-B 3034 MOSFETs do work. Also, down at the bottom, the IRL-B 8743 MOSFETs, those are reported working. I have not tested them myself, but they use them on like the RADs and the RAMPS FD and that type of thing. And then users have reported that the IRF 3205s that often come as an upgrade on certain RAMPS boards, those do at least turn on. I'm not sure how much current they can handle and how much temperature they would put out, particularly for the heated bed. But if you do find a board with those on it and you're paranoid about the heat bed, you can run an external MOSFET or just replace them. And the prices I have listed are for single units from DigiKey. And I did go ahead and order those to make sure they had them in stock and make sure they were okay. So this is what it comes like, or this is what it looks like when they come in the bags. This right here, these are the 3034s, I think the through-hole MOSFETs. And then this right here are the surface mount MOSFETs. Now, these are also the 3034s. These are in the D squared pack, which if you're looking at your RAMPS 1.5 or your 1.6, 1.5, that's going to be all 3 MOSFETs. 1.6, it's going to be the top 2 MOSFETs for the hot ends or the hot end in the fan. And then the bed MOSFET is actually a different, larger package, but it's functionally equivalent to the D squared pack, and that's not really an issue. Plus, that MOSFET's good enough that it can likely stay and you won't have a problem. Now, I personally think that desoldering and resoldering surface mount MOSFETs is easier than soldering and desoldering MOSFETs that are through hole, particularly if the board either has really thin traces, the holes aren't through plated, or they use a higher temperature solder, like a lead-free solder that takes a little bit of a higher temperature, because the board traces tend to go before the solder goes sufficiently that you can pull it out. So if you have any problems out there with knowing how to desolder surface mount components, let me know and I can put a video about that up there. You will just need a standard soldering iron, a bit of solder, some flux, and a pair of small pliers or tweezers. All right, so let's get to our TLDR summary. First, we have the top plane. What you need to do on the top is you take this second pin here and the third pin here, and you're going to bridge them with a little piece of solder. Just blob it right across there. That's going to bridge our 3.3 volt feed from the Arduino to the 5 volt. Next, we're going to take this pin right here, the second from the last, and we're going to jumper that over right here to this pin on the header. Then we're going to take the pin next to it and jump it right over here to this pin on the header. And those are going to be inputs for our thermistors. And that's because we don't have those same pins on the Arduino DUE as we do on the Mega, so we have to run these jumpers. Then we have the bottom side. So here's our 5-volt pin. It's 3 pins in. We need to cut that. Then we have these 4 pins over here that are completely different designations on the DUE and the Mega, so those have to go too so that we can hook up our thermistor jumpers on the other side. Then all the way down on the bottom, we have our aux 4 header where we're going to get rid of this 5-volt connection right here. So that way we're not tying our 3 and our 5 volts together and doing any weird short circuit stuff. Now what that also means is that all of these little 5-volt references on the RAMPS page where they are circled in orange, those are all going to be 3.3 volt outputs. And our 5-volt in yellow right there, our servo pin, and then the servo feed pin, and then the servo pins, that little header of 4 pins, that is not going to be connected to anything unless A, we jumper it, or B, we feed it with either 3 or 5 volts. So if you have a bunch of 5-volt peripherals that you need to use, that's a dandy place to use as a little distribution manifold. Next part, and this is important, are the MOSFETs. The MOSFETs that were originally specced on the ramps were actually meant for a 10-volt logic voltage. The original Mega puts out 5 volt, so it wasn't even sufficient, but they found that they did kind of turn on, but as we know, not well enough, because we have a lot of problems with these MOSFETs heating up and catching fire and that sort of thing. So they are certainly not going to work at 3.3 volts if they didn't work at 5. So those are going to have to be upgraded. And I provided in both this video and the last Duo video some alternatives that you might want to look at. In addition, I also have a video on parametric selection for MOSFETs if you dig back through those archives. Now, sometimes these RAMPS boards have upgraded MOSFETs, but usually they're not going to be good enough to run a hotbed at 3.3 volts. But they may be good enough to turn on at 3.3 volts. So if they are, then you can easily use an external MOSFET board to feed your hotbed. Or use it to feed your hot end. It doesn't care. Now, as far as end stops, the RepRap mechanical end stops will work just fine at 3.3 volts. They really don't care. Optical end stops and other types of fancy end stops, that's a different story altogether, and it varies drastically depending on what board you're using. So obviously I can't cover every single end stop that's created, but I'll touch on this a little bit in the additional nonsense section toward the end of this video, so look at the time index if you want to skip to that. And that brings us to our stepper drivers. As I mentioned in the previous video, the only stepper drivers that will work are either stepper drivers that derive their own logic voltage through an internal regulator from your VCC rail, or stepper drivers that can take a 3.3 volt logic level. That means your original silent StepStick TMC 2100 5 volts will not work. You can make a little adapter modifier for them with a bunch of diodes and get them to work, but pretty much all of the other stepper drivers that I've encountered worked. I would have to take them on a case-to-case basis, so make sure you check your data sheets for those particular drivers and make sure they will be okay at 3.3 volt logic. Now, your Allegro A4988s, they will work as long as you have 3.3 volt logic going into it, and that's what it's regulating down to. Also, your Texas Instruments DRV8825s, they work just fine. They don't care what the logic voltage is. And the other more fancy trinamic drivers, they will also work fine. Unless you get a mutant version that will only handle 5 volt logic, and there are a few of those floating around there. And there are actually like a dozen or so more types of drivers that use the StepStick format. I didn't check every one individually, so just, like I said, check your data sheet, make sure they're cool. Finally, if you want to use an integrated panel that's going to combine your display, your SD card reader, your beeper, stop button, and your encoder and selector button, the RepRap Full Graphics Smart Controller is already set up in Marlin to work with this board. There are some reports around of particular panels not working very well, but I have a couple here and they all seem to be just fine. Now, a couple notes on these panels. The drivers that they use for the LCD have to be fed extremely slowly. Otherwise, you get graphical glitches and all kinds of weirdness. Plus, the way that it's set up on the conversion ramps to Duo board, there are no hardware SPI pins on the aux header that the smart adapter uses. So you're using software SPI for both the display and for the SD card. Now that's fine for the display, but in terms of the SD card, software SPI runs a lot slower than hardware SPI. So if you wanted to do something with that, look in the additional optional mods section after this, and that'll show you how to break out your hardware SPI, and then you have just a matter of getting it configured. And speaking of the optional mods section, here we go. One that I strongly recommend is adding 5 volt power for your peripherals. You're going to need this if you're going to use that full panel display or anything else that needs 5 volts. I just jumpered this line straight from the DUE and added it on a DuPont connector, and you can just plug that in wherever it is you want to put it. I also mentioned that you can use a hardware eprom. This is an I2C adapter board. I bought a couple of these for, it was like, I don't know, maybe $9 for like 5 of them or 3 of them or something like that. Anyway, they're fairly cheap, and those will just plug right into your I2C header on your RAMPS board, and then you just have to configure them in Marlin. Now, if you want to use hardware SPI, there is no SPI on the aux headers like there is on the Mega. So you're going to have to run it from your SPI port, which is where your ICSP programming port was on the Mega, and then just run them out of the side of the board like this. And as you can see, I ran additional jumpers on top of my smart card board because I wanted to mess around with getting hardware SPI to work on just the SD card. That proved to be a little bit quirky just because of the macros that Marlin uses to set up all that stuff. They're trying to make it more modular, which will be very good because it's a huge twisted pretzel spaghetti mess of chasing definitions around headers if you want to get anything custom working these days. So just bear that in mind if you have this sort of setup in mind for yourself. What I actually prefer to do is build my own panel out of the individual components. So you could just take, this is a character display. I use that because it's a little bit quicker. And I plug that into a backpack that's an I2C backpack. So it'll convert all of those wires on top of the LCD into just 2 wires out. And then you just have to feed it the ground and the voltage. Then I run the SD card adapter right there on the bottom right into the hardware SPI. And you can take your encoder, wire that up to a little piece of PC board or just some jumper wires, and then assign those to whatever headers you have available. And for those of you who either want to convert to 24 volts and backfeed your Arduino from your ramps, or if you just want to make sure that you're not overheating your Arduino's power regulator, you can take one of these little DC-DC switch mode regulator cards. They only cost a couple bucks a piece, and you can hook that up to your board between the ramps and the Arduino where your D1 diode is to backfeed a regulated voltage into that to take a lot of the load off of your Arduino's regulator. As far as communication goes, there are a lot of these types of modules that you can get working with the ramps. I'm not going to go into that because it's a whole other headache, and these naturally run at 3.3 volts. They come, if you can see, on top of an adapter board that has a regulator that knocks the 5 volts down. Obviously, you don't need that, but you may have to mess around with other pull-up, pull-down resistors. It really depends on the setup in the board. All right, now here's the world's fastest 24-bit conversion tutorial. Ready, go. All right, on our standard ramps boards, what we need to do is make sure that everything is compatible with 24 volts, coming in from here and then going all the way out to your steppers. That means specifically you have to make sure that your thermistors are compatible with 24 volts. So if you flip them over and it says 16 on the side, no good. If it says 30 on the side, like the other ones do, you're fine. Moving on from there, each of these are your capacitors that filter out your V-mote voltage that's going to run your motors. You have to make sure that this says, usually if they're upgraded, it says 35 volts here. If it says 16 volts, no good. You have to either replace them or get a board that already has them upgraded. And it's a pain in the butt to replace them because they are surface mount and you have these headers in a way to melt with your nice big fat soldering iron. Then there's a diode right here, which is your D1 diode buried all the way down at the bottom. You either have to cut that or desolder it from the bottom and then pull it out, because that's going to take the voltage from your high voltage rail here, feed that down through the board and into your Arduino Mega, and your voltage regulator cannot take 24 volts and convert it down to the level that your Arduino is going to use. So you'll have to power your Arduino separately. Now at the ramps 1.5 and 1.6 boards, ignore the fact that I pulled one of the MOSFETs off of here. Everything is already set up for 24 volts and you don't have to worry about it, except this is your D1 diode right here. You either have to desolder that or just pull it right off with a pair of pliers. As you can see right here, I yanked this one off, and that's all you have to do for 24 volts. You don't have to worry about polyfuses because right here are your fuses. They're surface mount standard fuses, and they're rated at 32 volts, I believe. Most of the time they are, and all of your capacitors are already good to go. It also applies that you cannot feed your Arduino from your 1.5 or 1.6 board, again because of the regulator. So once you pull that diode off, you're going to have to power this board separately, either via USB or through the DC jack, or by backfeeding one of the other pins somehow. With both of these, you can wire up an external regulator, like this one or this one, and you have your voltage come into this side, And then your voltage out, you're going to feed it into the Arduino through the output pin for your D1 diode. Then that's going to go down to your RAMPS board and power that. Same thing on the 1.5, 1.6, but instead of having a through-hole connector, you have to solder it to the out pin on your D1 diode solder pad, since these are surface mount. That regulator is then going to knock the voltage down from 24 to a more usable level. You can pick whatever, but I would recommend something like 9 volts because you want to put as much of the strain of dropping that voltage onto this board as possible, since this is a switching regulator and it's not going to heat up like the regular regulator that is on your Arduino board, which is right up here, because that puny little thing always pops. And you can see my 5-volt regulator, I put a heat sink on top of that because that will help it dissipate a little bit of the heat, but if you drop the voltage down, that's not completely necessary anyway. Cool. So that covers all of the modifications. Now let's talk about additional nonsense. I just called it nonsense because this is a hack after all, and everything's not going to work out of the box. So here's just a sneak peek into either some of the things you may have to do to get your favorite peripherals running, or things that you need to really watch out for so you don't cause yourself any damage. And remember, this is a hack. We are not prepared for legacy peripherals, so be careful and never run a 5-volt signal into a 3.3 volt input because you will blow it. That includes 5-volt optical end stops, because these are meant to take a 5-volt voltage into the top and then they output a 5-volt signal, so they will not work. Going from a raw 5 volts to a 3.3 volt input is always going to be a bad day. And I just mentioned those optical end stops because they're popular. That also applies to your servos, your leveling probes, at least the older ones that aren't 3.3 volt compatible, thermocouples, piezo sensors, comm peripherals that might be 5 volt, some types of lighting that might have PWM in-out controls and sensors, etc., etc., etc. So better safe than sorry. Now, if you do have optical end stops, is it possible to get them working? Sometimes. It really depends on the board. And again, I hate to beat this horse to death, but it really is a case-by-case basis. You'll have to look at the schematic of your board, see if A, those end stops will run at 3.3 volts, B, if they don't, what it'll take to convert the signal down to 3 volts for your Arduino, and then make the accommodations. As I mentioned before, those accommodations could be some kind of a pad or a voltage divider, or one of these, which is a multi-channel bidirectional level shifter. Now what that does is it takes our 5 volts that goes in, shifts it to a safe level, and then spits that signal out as a 3.3 volt output. Similar to our power regulators, but those are for DC voltages. These are for AC voltages. It's not the same thing, and you can't use one for the other. Now, this is all the fault of the Arduino DUE not using a CPU or MCU that has 5 volt tolerant pins. Some boards, like the RAMP for example, have accommodated this by putting onboard level shifters for particular pins, while other boards, like the smart ramps for example, they have not. So using a smart ramps is not going to solve your peripheral issues. Now here comes the second issue. While we know going from 5 volt to 3.3 volt is bad, going from 3.3 volt to 5 volt, sometimes it works, sometimes it doesn't. A lot of times you'll be just fine, but sometimes the 3.3 volt high signal just isn't enough to cross the threshold for the 5 volt peripherals. So if you have something that's a little bit stubborn, taking a 3.3 volt logic signal powered off of 5, you can drop that power down by 1 diode, and usually that's enough to knock the reference voltage down so that when you have your threshold that you have to meet, it moves that down low enough so that it can be triggered by 3.3 volts and everybody's happy. Also, you recall that I mentioned in the last video that the DUE cannot put out as much current as the Mega did. So if you get a situation where you're randomly rebooting or shutting down, you're drawing too much current and you should rethink what peripherals you have plugged in. Also, many of the DUE clones used incorrect values for some of the resistors, and they're prone to connectivity problems and other reboot problems. Unfortunately, you won't know that until you either get the board or find somewhere in the forums where somebody has pointed you out to one that works or didn't work. Do not trust the Amazon reviews underneath these boards because they tend to reuse reviews for one board for another board, even though they're made by completely different manufacturers, but they have the same name, so you have been warned. So those are all the issues that I could think of either off the top of my head, looking through the schematics, or when I was doing the process. And I did do it twice, and I got it running. And like I said, I picked the method that I thought would be the most friendly, user-friendly, and that would work best with the profile that's built into Marlin 2. Now that brings us to a completely different issue, which is installing Marlin 2, which is their 32-bit branch, which is officially not out yet. It's still in the experimental phase, and that code base changes every single day as they're uploading or as they're updating and getting more features working for the various boards that are out there. Now, like I said, this does work, and I do have it running on my printer. I had several successful prints after everything was set up and calibrated. So all of the fringe cases and the problems don't have to do with the mod themselves, but rather what you're plugging in and out of the board. So if you're trying to make it as simple on yourself as possible, do the mods, don't plug anything goofy into it, and then just use remote printing, like a Pronterface or Octoprint or whatever it is that you prefer using. And use the basic parts that you know are going to be compatible, like mechanical end stops and 3.3 volt compatible stepper drivers. And as I mentioned before, I kind of dread becoming an unofficial like resource / product support for this mod because it is a hack and it is iffy. It is a little bit dangerous if you don't do things right or if you're lazy about it, and you have the potential of wrecking your gear or frying the USB bus on your computer if you plug things in wrong or do the jumpers wrong or something like that. So safety first, and I will try to answer some questions in the comments, but with the virtually infinite number of different variations, I don't have time to hit on everything that's out there in the market, and I have an ever increasingly large pile of videos that I need to get edited, as well as working on the projects themselves for new things. So I'll do the best I can. This all takes a huge amount of time. If you want me to be able to keep doing this, remember I always have support links in the video description below. So that's very much appreciated to keep this channel going. And as I always say, until the next video, get out there and make something awesome. Or get out there and mod something awesome. And then take your mod and make something awesome.